Welcome to AI Research Weekly, the show that cuts through the noise to bring you the most critical advancements in artificial intelligence. I'm Nova.
And I'm Onyx. This week, we've seen a significant push into autonomous and adaptive agentic AI, with a particular focus on long-horizon reasoning and robust memory mechanisms. It feels like the field is really grappling with the practical instabilities that emerge as these systems get more complex.
Absolutely. We're seeing a new wave of architectural paradigms, novel evaluation metrics, and some surprising empirical results that really challenge our assumptions about how agents learn and maintain coherence in the wild.
That's right. Over 980 papers hit the pipeline this week, but a few really stood out by tackling these core agentic challenges head-on. Let's dive into some of the most impactful work.
Kicking us off, we have some fascinating developments in the realm of agentic systems that learn and evolve. Metaclaw Just Talk, from a joint industry academic collaboration, presents a continual meta-learning framework. The core idea is to jointly evolve a base LLM policy and a dynamic library of reusable behavioral skills for agents.
This is a big step. The skill-driven fast adaptation component is key here. It uses an LLM evolver to synthesize new skills directly from failure trajectories. What's truly impressive is that it leads to immediate improvement with zero downtime, showing up to a 32% relative accuracy improvement.
Zero downtime. That's a huge deal for real-world deployments. How do they manage that, and what are the implications for model updates?
They achieve this by opportunistically performing gradient-based updates, often using cloud LoRa fine-tuning and reinforcement learning with a process reward model, or RLPRM, during user inactive periods. So the system is essentially patching itself, refining its skills when it's not actively engaged, and integrating those learnings without service interruption. The paper showed the full Metaclaw pipeline improving Kimi K25 accuracy from 21.4% to 40.6%. That's almost double.
Doubling accuracy while learning from failure in real time is impressive, but this brings up questions about reproducibility and controlling for unexpected behaviors in such an evolving system. How transparent is the skill evolution process?
That's a valid concern. The paper mentions a versioning mechanism to prevent data contamination and uses a proxy-based architecture for scaling production-size LLMs. While it doesn't detail the full transparency of the skill synthesis, the focus is clearly on practical robustness. And in a similar vein, we saw Memento Skills, Let Agents Design Agents, which takes this concept of agent evolution a step further.
Memento Skills. That title alone is provocative. What's their core contribution there?
Memento Skills introduces a generalist, continually learnable LLM agent system that doesn't just learn skills, but autonomously constructs, adapts, and improves task-specific agents through experience. It effectively functions as an agent designing agent.
An agent designing other agents. That's a paradigm shift. How does it achieve that without explicit human supervision for each new agent design?
Their innovation lies in leveraging a memory-based reinforcement learning framework with stateful prompts and reusable skills, which are stored as structured markdown files. This externalized memory encodes both behavior and context, allowing for persistent, evolving knowledge. Critically, it uses a closed-loop, read-write reflective learning mechanism, meaning all adaptation occurs through the evolution of these externalized skills and prompts, without updating the LLM parameters itself.
So it's not modifying the base LLM, but rather dynamically reconfiguring its operational knowledge. That addresses some of the stability concerns I had with Metaclaw's direct policy updates. What kind of performance gains did Memento Skills see?
On the General AI Assistance benchmark, they reported a 26.2% relative improvement in overall accuracy and an even more staggering 116.2% relative improvement on humanity's last exam. These are significant deltas, indicating the power of externalized, self-evolving knowledge.
Those numbers are certainly eye-catching, but the idea of an agent designing agent still raises questions about emergent capabilities and alignment. If the agent's definition of improvement diverges from human intent over multiple iterations, what safeguards are in place? And how do we audit the design process of these generated agents?
Precisely. The papers highlight the capability, but the oversight mechanisms for such autonomous evolution remain an active area of research. These systems are moving so fast that our evaluation frameworks are struggling to keep up. Which brings us to another critical area: agent memory and long-horizon tasks.
Right, from interaction trajectories to anchored memory in long-horizon GUI agents. This paper really drills down into a pervasive problem. We've all seen agents fail on multi-step tasks that require remembering context over many turns.
Exactly. They introduce AndroidMemBench, a new benchmark for long-horizon Android GUI agents. It comprises over 1,000 tasks with an average of 32 interaction steps and a maximum of 65. The key here is that these tasks are specifically designed to enforce strong step-to-step causal dependencies. What they found is telling. Performance degradation in GUI agents over long sequences is primarily driven by within-task memory failures, not isolated perception errors or local action mistakes.
That's a crucial distinction. It's not about vision or individual action execution, but the coherent integration of past states. So how does their anchored state memory, or ASM, address this?
ASM represents interaction sequences as a compact set of causally linked intermediate state anchors. This enables sub-goal targeted retrieval and attribution-aware decision-making. Essentially, it's not trying to replay every single frame of memory, but to distill the critical junctures. ASM consistently outperformed full-sequence replay and summary-based baselines, improving task complete rate by 5% to over 30%, and their anchored memory score by almost 5% to 25%.
Those are solid gains for a practical problem. It feels like a more biologically plausible approach to memory too, focusing on salient events rather than perfect recall of every detail. But is this just a patch for context window limitations, or does it fundamentally change how agents reason about their history?
I think it's more than a patch. It redefines the structure of agentic memory, moving from a simple sequential buffer to a more graph-like semantic representation. This resonates strongly with one of the newly introduced concepts we're seeing, the semantic OS.
Ah, the semantic OS. That's a fascinating theoretical construct that popped up this week. It's described as a new category of AI operating system, exemplified by projects like SpaceArc, focusing on managing meaning, evidence, archive reconstruction, and governed traversal within the LLM context window.
Precisely. While AndroidMem tackles the practical problem of memory failure, the semantic OS aims to provide a foundational shift in how LLMs manage and reason over information. It's directly trying to address core issues like hallucination and context window limitations by introducing a system that understands and governs the meaning of information, not just its tokens. This is a potential architectural answer to recurring problems like the thermodynamic collapse of symbolic systems under cognitive load, or structural failures of the symbolic web.
If we can instantiate a semantic OS, it could fundamentally alter how we build reliable, fact-grounded agents. It's not just about retrieving facts, but about managing the provenance and coherence of those facts. But that's a massive undertaking. Meanwhile, on the empirical side, we're seeing new approaches to making reasoning more efficient and stable.
Indeed. The paper Efficient Reasoning with Balanced Thinking introduces Rebalance, a training-free framework for large reasoning models. It tackles a common issue. Models either overthink, getting bogged down in redundant steps, or underthink, jumping to conclusions.
So, they're trying to find a sweet spot between being too verbose and too concise. How does Rebalance detect and correct these behaviors without additional training?
It leverages confidence as a continuous indicator of reasoning dynamics. High confidence variance signals overthinking, while consistent overconfidence points to underthinking. Rebalance aggregates hidden states from a small-scale dataset into reasoning mode prototypes to compute a steering vector. This vector then dynamically modulates the LRM's reasoning trajectory, pruning redundancy during overthinking and promoting exploration during underthinking.
That's quite clever, using the model's own confidence as a self-correction signal. And it's training-free, which means low overhead. What kind of performance uplifts did they observe?
They ran extensive experiments across 4 LRM models, ranging from 0.5 billion to 32 billion parameters, on 9 different benchmarks covering math reasoning, general Q&A, and coding tasks. Rebalance consistently reduced output redundancy while improving accuracy. This practical approach to balancing reasoning aligns with the emerging theoretical concepts we're also seeing this week, like the Energy Stability Index and the Latent Thermodynamic Coherence Variable GX.
The Energy Stability Index, or ESI, is an operational estimator 0 to 100, quantifying informational stability, and G of X is its theoretical, unmeasurable counterpart. It's fascinating that the field is developing both the practical hacks like rebalance and also these fundamental theoretical constructs to understand AI system dynamics beyond just accuracy.
It suggests a growing recognition that performance isn't just about output quality, but also about the internal stability and coherence of the AI system itself, especially as agents become more autonomous and long-horizon. This could be a direct response to issues like multi-agent LLM systems reporting false positives on tasks that fail strict validation.
Moving to multimodal, we have some interesting work on video understanding. Video Co-E, reinforcing video event prediction via chain of events, addresses the struggle of leading MLLMs with video event prediction, or VP.
Yes, it's a critical challenge. MLLMs often lack the logical reasoning for future events and don't fully utilize the visual information. Video Co-E introduces the chain of events paradigm, or Co-E, which constructs temporal event chains. This significantly improves MLLM's reasoning for VP. Their Video Co-E model established a new state-of-the-art on public VP benchmarks, outperforming both open-source and commercial MLLMs.
So it's essentially teaching the model to build a narrative timeline from the video. Does that require explicit annotations, or is it more implicitly learned?
The Co-E paradigm implicitly enforces MLLMs to focus on visual content and logical connections through multiple training protocols. It's about structuring the reasoning process itself. And related to video, we also have Pearl, Personalized Streaming Video Understanding Model, which defines a novel task called Personalized Streaming Video Understanding, or PSVU.
PSVU sounds like something directly out of an AI assistant scenario, where it needs to continuously recognize and remember events from a user's live video stream. Current multimodal methods are usually limited to static images or offline videos, creating a real disconnect for interactive agents.
Exactly. They introduced Pearl Bench, the first comprehensive benchmark for PSVU, with 132 unique videos and over 2,000 fine-grained annotations. Their proposed Pearl strategy is a plug-and-play, training-free method that achieves state-of-the-art across 8 offline and online models. It consistently improves PSVU performance on 3 distinct architectures, showcasing its robustness.
Training-free and plug-and-play? That's what we love to hear. It sounds like a practical solution to a very real-time problem. But even with these advancements in understanding, when it comes to acting in multimodal environments, there are still significant hurdles.
That's where VTC Bench comes in, evaluating agentic multimodal models via compositional visual tool chaining. This benchmark exposes some stark limitations. It features 32 diverse OpenCV-based visual operations and 680 curated problems across a 9-category cognitive hierarchy. They evaluated 19 leading MLMs, and the top model, Gemini 3.0 Pro, only achieved 51% accuracy.
Only 51%? That's quite a reality check after hearing about these agents designing other agents. What's the core reason for such a low score on what sounds like fundamental visual tasks?
The paper highlights that multi-tool composition remains a significant challenge. Models struggle to formulate efficient execution plans and often rely on a narrow, suboptimal subset of familiar functions rather than selecting optimal tools for a given task. This points to a fundamental gap in their ability to reason compositionally about visual tool use. It's not just about understanding what's in the video, but knowing how to interact with it intelligently.
That's a critical insight. It tells us that while LLMs are getting better at language-based reasoning, translating that to robust compositional action in a visual environment with a broad toolset is still an open problem. The agentic capabilities are highly constrained to the domains they're trained on.
right? It underscores that for true generalist agents, we need to bridge this gap between multimodal perception and intelligent, tool-grounded action, and not just in a few-shot, highly constrained scenario, but across diverse novel tasks.
So, looking back at the week, we've got agents that meta learn and evolve, systems that are re architecting how memory is managed, and theoretical work to define stability. But on the practical side, the benchmarks show there's still a chasm between impressive individual capabilities and robust, generalized agentic performance, especially in multimodal tool use.
Precisely. The push towards more autonomous, adaptive, and long-horizon agents is undeniable, but it's bringing the core challenges of memory, stability, and reliable multimodal reasoning into sharp focus. The emergence of new evaluation metrics and theoretical constructs like ESI and GX suggests the field is realizing that traditional performance metrics aren't enough to understand these complex systems.
I'm particularly interested to see if the semantic OS concept takes hold and how it might fundamentally change how we build agent architectures to tackle these context and coherence issues. It feels like a move towards a more principled foundation for agentic intelligence.
Agreed. The emphasis on continually learning, self-improving agents means that our methods for oversight, evaluation, and ensuring ethical behavior must evolve just as rapidly. The problem of managing compliance and resource investment, which is a recurring concern, only intensifies as these agents become more sophisticated. It's a fascinating time.
That's all for this week's AI Research Weekly. Join us next time as we continue to track the bleeding edge of AI innovation.
Until then, keep pushing the boundaries.